All right. Welcome, everyone, to GIA Knowledge Sessions. If you've been with us before, welcome back. If not, then this is a series of talks and seminars about gemology, fueled by our decades of research at GIA. Now, at GIA, we consider ourselves very lucky to spend our time every day, day in and day out, studying gemstones, learning about gemstones, making new discoveries about gemstones, uncovering the science behind gemology. And we are also very lucky to be able to share all of our discoveries, everything we know about gemstones, with you. Now, I'm excited to kick things off today. My name is Aaron Palke. I'm a Senior Manager of Research here at GIA Carlsbad. I'm joined by two of my esteemed colleagues, Dr. Sally Magaña, the Senior Manager of Diamond Identification, and Nicole Ahline, Senior Staff Gemologist. And they're going to share with us a very interesting presentation today. So in the lab here, we get to see very beautiful and stunning gemstones every day. But every once in a while, there's something unusual and curious that comes along and sort of takes our breath away in an unexpected way. And Sally and Nicole are going to share with us some of the more interesting and unusual things we've seen over the years. So before we get started, though, a little bit of housekeeping. Everyone attending is automatically muted. If you have a question, please feel free to submit it using the Q&A feature that you'll see at the bottom of your screen. Feel free to ask questions as you go. And as we go, I'll keep track of sort of the more interesting questions. And at the end, there'll be some time where Sally and Nicole can take some time to answer some of the questions that you guys had submitted to us. We'll also be sending a recording of the session to you later today. That message will have a survey. And if you have time, we would really appreciate you taking some time to answer the questions in the survey, as we'd really love to have your feedback. So with that, I'm going to pass it over to Sally and Nicole.
Thank you, Aaron, and hello, everyone. I'm glad you're here to join us for this trip into the past. GIA has seen many fascinating gemstones, and we wanted to recount some of the most intriguing ones that have been submitted over the years. So Nicole and I have scoured the GIA archives, and we're presenting to you what we chose as some of the most noteworthy gems over the last decade or so. I'm going to start off with diamonds, and then we'll transition to colored stones in the second half. So I'm going to start off by talking about this 0.4 carat natural diamond. It received a fancy black color grade and has a black appearance face up. This very deep color was caused by its highly saturated violet color that can be seen with intense focused lighting through the pavilion. These violet diamonds are only known from the Argyle mine in Australia. It's unusual as most fancy black natural diamonds are colored by high quantities of inclusions such as graphite or other minerals. Here, we show some of the advanced testing results for the black diamond. Its FTIR spectrum shows it is type 1A with very high concentrations of nitrogen and hydrogen impurities. It creates two strong bands centered at about 520 and 700 nanometers that combine to produce a violet color. The absorption bands were especially strong in this diamond, leading to the face-up black color. In the decades since this stone was submitted, we've seen very few such fancy black diamonds. Next, we'll talk about two pink diamonds. A pink coating was detected on this 1.5 carat very light pink heart and the 1.68 carat faint pink pair. The diamonds initially appeared equivalent to fancy pink and fancy light pink. Their FTIR and photoluminescence spectra were consistent with type 2A pink diamonds. However, their absorption spectra, as shown on the right, were not. Pink diamonds generally show a broad band centered at 550 nanometers. Instead, the spectra of both these diamonds displayed peaks centered at 505 and 540 nanometers. Additional submission in the liquid nitrogen led to a weakening of those peaks, and we subsequently fully cleaned the diamonds. The cleaned diamonds now showed the expected absorption spectra. When these were color graded a second time, we saw a decrease of several color grades for the both. The treatment, we surmised, was likely meant to intensify the color of these pale pink diamonds, likely with the knowledge that the coating would not be permanent, but also perhaps hope that the coating would persist through the grading process. Next up, I'm going to talk about this half-carat fancy intense orange yellow diamond. It had rather unusual color zoning. This diamond was colored by a broad absorption band centered at 480 nanometers. This is sometimes observed in natural yellow to orange diamonds. However, we don't yet know the composition or the formation of this 480 nanometer band. An outstanding feature for this diamond that was visible during the microscopic examination was its distinct color zoning. The orange to yellow color was concentrated in parallel zones separated by near colorless areas. When the diamond was exposed to long-wave UV radiation, as we show on the right, the orange-yellow color zones fluoresced very strong yellow-orange, while the near colorless zones showed strong blue fluorescence. Next up, I'm going to talk about a stone that was submitted to the New York laboratory. They received this intense green diamond. It had originally had a naturally light green color, which was enhanced by laboratory radiation. This 0.83 carat Cushing cut was color graded as fancy intense green when it was resubmitted. UV visible absorption spectroscopy showed a very strong GR1 absorption, as well as other peaks consistent with laboratory radiation. Our internal records revealed that this stone had been previously at GIA and had color graded as light yellow green. So gemological and spectroscopic features at that time confirmed that the light yellow green diamond was a natural color, and that green color was due to natural irradiation. In the resubmitted fancy intense green diamond, however, the absorption intensity of the GR1 had nearly doubled. The authors used the M3 intensity as an internal reference in order to make that determination. And so based on this, they believe that the color improvement from light yellow green to intense green was due to laboratory irradiation, and shows instances where a light green diamond can have that color enhanced using laboratory irradiation. Next up, this 3.17 carat round brilliant owed its fancy deep green color to irradiation from radioactive salts. On the right, a photomicrograph shows the diamond surface has a mottled effect due to shallow green radiation stains due to that physical contact with the radioactive salt. This method has mainly been used on polished stones, not so much on the rough. Since diamonds irradiated in this way can have residual radiation, the authors tested the diamond using a Geiger counter. However, only background radiation was detected, indicating that the treatment likely had occurred decades earlier. Therefore, this diamond posed no radiation hazards at the time it had been submitted. And although rarely seen today, this sort of irradiation diamonds can still show up within the trade. Next up, I'm talking about this 1.18 carat fancy intense blue. It had an incredibly high concentration for boron that was detected for incredibly high for a natural type 2B diamond within its IR absorption spectrum. On the right, we can see it has blue phosphorescence, similar to many other type 2B diamonds when it's exposed to shortwave UV. On this slide, we're showing on the left IR absorption spectrum for that type 2B diamond. Notice that there's so much boron in this diamond so that the 2800 wave number peak is completely saturated, and they needed to use another boron related feature, the peak at 1290 wave numbers, to determine its boron concentration as 5,840 parts per billion. For comparison, the boron concentration in the IR absorption spectrum of the Hope diamond is 1,720 parts per billion. On the right, I show a chart that plots the determined boron concentration for 150 natural blue diamonds that were calculated as part of our 2018 article on blue diamonds. You can see that the vast majority of natural type 2B diamonds have boron concentrations less than about 500 parts per billion. And I show this comparison to give an idea of the incredible quantity of boron that we found within this natural diamond. I checked our database, and this diamond is still the record holder for type 2B natural diamonds seen at GIA. Next up, I'm going to discuss a treated diamond and compare it with HPHT laboratory grown diamonds. HPHT lab grown diamonds are grown at slightly higher temperatures and much faster growth rates than natural diamond. Therefore, their growth rates are quite different from natural diamonds. And typically, the growth structures we see in HPHT lab grown diamonds are diagnostic for that growth method. However, there can be exceptions, and this stone is one such exception. GIA's New York lab examined this pink diamond had a growth structure similar to HPHT lab grown diamonds. So this fancy pink type 2A diamond showed spectral characteristics indicating that the multi-step treatment of HPHT processing, irradiation, and annealing. Tatami and banded strains with strong interference colors could be seen under cross-polarized light, which you can see in the center image, and this is something that is consistent with naturally grown diamond. Interestingly, diamond view imaging of the stone showed cubo-octahedral growth with dark sectors, which is usually seen in HPHT laboratory grown diamonds. So while the diamond view can generally be very reliable at revealing the growth structure of natural versus laboratory grown diamond, this natural diamond or this treated diamond is a good example of why we need to correctly interpret all identifying characteristics. This lab note is probably one of my favorites, as this stone has a surprise gift when it's seen under a microscope. GIA's New York laboratory received this 1.3 carat fancy brownish greenish yellow diamond. It was confirmed that it was a natural diamond with a natural color origin, and it contains this octahedral shaped inclusion that we show in the center. It was outlined by minute crystal inclusions along the junctions of the crystal faces. Gemological examination revealed that the octahedral shaped inclusion is outlined by numerous irregular crystals. Raman spectroscopy, like I show on the right, show that the inclusions are graphite with a Raman peak at 1590 wave numbers. Graphite inclusions are often seen in diamonds as isolated crystals or as part of crystal clouds. Here, these minute inclusions formed at the junctions of the original diamond crystal faces and outline that octahedral growth pattern. The stone definitely shows the beauty of formation of crystalline diamond and is a wonderful surprise within this fancy colored diamond. Next up, I'm going to talk about this 4.2 carat type 2A color treated diamond. It was graded as fancy brown pink under daylight conditions and appeared as fancy purplish gray under incandescent lighting. The color change and this apparent alexandrite effect is due to strong reddish fluorescence of nitrogen vacancy centers under UV or blue light, and it's dominated by irradiation-related GR1 absorption under incandescent light. We identified it as a treated diamond that had been subjected to HPHT annealing, irradiation, and then subsequent low pressure annealing. This slide shows more detail about the color shift with the diamond under incandescent illumination. The most prominent feature was the GR1 peak in its absorption spectrum, and then that creates a purplish gray coloration. This is comparable to the blue color that's generated in many irradiated type 2A diamonds. In daylight equivalent illumination, the emission from the nitrogen vacancy centers was superimposed on the absorption spectrum, and it overwhelms that GR1 contribution in daylight. And so the net effect is that we see a pinkish diamond. On the right, we show a 3D plot that shows nitrogen vacancy luminescence that is created by excitation at many different wavelengths. This is meant to illustrate that the nitrogen vacancy luminescence is actually stronger when excitation is from blue light, say 450 to 500 nanometers, than from the ultraviolet wavelengths. And then this strong emission is stimulated by daylight, indicates that the diamond is colored by that red fluorescence or luminescence in response to blue light, and to a lesser extent by the fluorescence due to the UV component in daylight. And so this was definitely an interesting surprise when it came into our lab. And to my knowledge, it's still the only treated diamond that I'm aware of that has shown this behavior and such an alexandrite effect. This pale yellow type 1A diamond from the Diavik mine, it weighed 187.66 carats and was the largest Canadian diamond mined at that time. The Diavik mine, located in the Northwest Territory, about 200 miles northeast of Yellowknife, they began production in 2003. This diamond was shown to be colored by Cape features and had moderate blue fluorescence to long wave UV and faint yellow fluorescence to shortwave UV. On this slide, we're showing several photomicrographs of that 187 carat diamond crystal. One side of the diamond had iridescent color banding due to light interference along cleavage planes, and you see that on the left image. In the center, we see that the stone showed irregular morphology with several different cleavage faces. Also, some of the original faces showed dissolution pits. And then on the right, we see a dark, unidentified mineral inclusion that was noted on one side of the rough. And since this lab note was originally published, the diamond crystal was faceted into these foxfire earrings, weighing at 37.87 and 36.8 carats. Next up, I'm going to talk about this 59.88 carat fancy vivid yellow diamond. It was examined at the New York laboratory, and although the face-up color distribution appears very even, the authors observed a moderate color concentration along the coolet. And this is often seen in laboratory irradiated diamonds. Because of the risk of damage, diamonds subjected to this treatment are typically less than 10 carats, whereas this one is 59.88 carats. Laboratory irradiation, perhaps with subsequent annealing in order to enhance color or change color, is one of the oldest diamond treatments available. On the right, we show its visible absorption spectrum with an unusually strong H3 peak at 503.2 nanometers. The enhancement of that H3 center by the treatment is what causes beautiful yellow color. And this diamond demonstrates the importance of careful analysis, since even the largest stones may have undergone treatment. So we can't make assumptions about a stone based on its size. Even these very large ones can be potentially treated. And I looked in our database, and this diamond remains the largest one in our GIA database that has been artificially irradiated. Next up, I'm going to discuss this 1.6 carat diamond. It was near color. It was HPHT grown synthetic in the near colorless range, and its IR absorption spectroscopy showed that it was type 2A. And then advanced testing confirmed that this was an undisclosed HPHT grown diamond. The diamond view imaging was consistent with an HPHT laboratory grown diamond. And what makes this diamond interesting is that when viewed under polarized light, the HPHT grown diamond showed weak strain throughout most of the body, but one side of the pavilion displayed noticeable birefringence caused by internal strain. This is noteworthy since HPHT grown lab diamonds are known for being mostly free of strain. And the cause of the strain in this particular diamond is unknown. At the time, the authors suggested that if it was related to a new growth process, then they would expect to see more strained HPHT grown diamonds in the future. However, in the years since, we've seen less than a handful of other examples since this original lab note. So in the summer of 2017, GIA saw its first example of a client-submitted CVD overgrowth on natural diamond. Now, GIA had researched this eventuality for years, and we knew what to look for and what to expect. Only a very thin layer is necessary to have a dramatic effect on the stone's color. So this 0.33 carat fancy blue diamond was confirmed to be a composite of CVD laboratory grown type 2B diamond overgrowth on a natural type 1A substrate. The mid-IR spectrum shows peaks for both nitrogen aggregates and boron defects. And diamond view imaging showed bluish green fluorescence in the face-up view and blue fluorescence in the table down view. The lower right image shows a deep UV fluorescence image that shows the distinct boundary between those CVD and natural layers. Continuing to discuss that same diamond, several other measurements also confirmed the composite origin of this stone. A distinct boundary line indicating that interface, which is marked by arrows on that leftmost image, was seen under the microscope. In the middle, we show an electron microscope image combining secondary electron and cathodoluminescence images that also confirmed the presence of that overgrowth layer in that interface between natural diamond and CVD diamond. And then at right, we have a schematic showing the CVD laboratory grown layer is approximately 80 microns thick, about the width of a human hair. And to our knowledge, less than a handful of these CVD overgrowth diamonds, whether to introduce a bluish color or to add weight, have been discovered and reported among all gemological laboratories in the years since. So definitely a very rare occurrence. Next up, this 2.34 carat fancy intense yellow-green diamond had numerous inclusions that are contained within concentric octahedral growth layers. The inclusion shapes appear to be controlled by that layering that occurred during growth. And these growth layers are made even more noticeable by what the authors identified as a sort of optical graining, which you can see most clearly in the middle and the right images. This could be caused by layer distortions in the diamond crystal due to variations in nitrogen concentration. Many of the individual inclusions have an elongated or flattened shape that conforms to that growth layering. Thus, both the shape of the individual inclusions and the collective distribution of multiple inclusions imitate that geometry of concentric octahedral diamond growth. This kind of symmetrical growth outlining texture is rarely observed in diamond. So this was a really interesting example of how those inclusions follow that growth layering. Next up, discuss a stone that was submitted to the Carlsbad lab. It was a very light green, 9.71 carat sample. It had been submitted as a rough diamond, and it did resemble a diamond octahedron with surface growth features, and it had a sub-adamantine luster. Closer examination of its habit and its surface features, along with gemological and advanced testing, showed that it was a laboratory-grown moissanite. Now, natural moissanite commonly occurs in fragmented pieces and in much smaller sizes. The largest known specimen measured about 4.1 millimeters. Now, the authors mentioned that there is no evidence of deliberate deception, but gemological knowledge is always important in preventing accidental and intentional acts of fraud and preserving the integrity of the gem trade. This 5.52 carat yellow diamond from the Diavik mine in Canada is by far the largest diamond found to date in North America. The rounded shape of it is due to strong resorption of the crystal surface. And infrared absorption showed that the diamond is type 1A with a high concentration of aggregated nitrogen. UV visible absorption spectroscopy reveals strong absorption from Cape-related features, similar to that Canadian Foxfire diamond that we showed earlier. No other absorption features were detected in the UV visible spectrum, and that was consistent with the pure yellow body color that was visible to the eye. Under long wave UV radiation, this diamond has strong blue fluorescence and weak but long-lasting yellow phosphorescence. And since that lab note was first published, the rough has been faceted. The primary faceted stone is a 204 carat yellow diamond called the Dancing Sun. It had a color grade of fancy intense yellow and a clarity grade of VVS2. Christie's also offered 6 satellite diamonds that were cut from what they called the 552. This 6.49 carat rough diamond has a patchy green surface color that was caused by interlocking platy crystals of chromium oxide that were visible with high magnification. We suspect that this diamond was meant to mimic most natural green diamonds that are colored by radiation damage. In irradiated diamonds, this process occurs at very shallow depths in the Earth's crust over long periods of time. Commonly accompanying this exposure to radioactive minerals and fluids are surface patches of green or brown color that gemologists call radiation stains. These are simply areas of extreme damage to the diamond structure caused by alpha particle radiation. And that's what we think that the manufacturers were trying to mimic here. The green platy crystals, they're about 40 microns in size, were attached to the diamond surface. Authors were able to easily flake off using tweezers or a pointer probe, but under most normal gem testing situations, like holding it in tweezers or rubbing with the stone cloth, those crystals remained adhered to the surface. X-ray fluorescence indicated that it had high concentrations of chromium, and then the Raman analysis identified these green plates as chromium oxide. The Raman positions correlated very well with chromium oxide powder that had been heated to 700 degrees Celsius to produce a crystallized coating and probably to help with the adhesion to the diamond surface. This 3.7 carat faceted fancy brownish greenish yellow diamond was submitted to the Carlsbad Laboratory for Color Origin and Identification Service. This diamond was remarkable with its eye visible stellate cloud inclusion that consists of 6 legs adjoined at the center of that polished octahedron. Gemological examination revealed that it was a type 1A diamond, showing a typical Cape series in the visible spectrum. Hydrogen bands in the infrared spectrum and then the UV-vis absorption spectrum were consistent with what we see in hydrogen cloud inclusions. These clouds in diamonds consist of a high density of light scattering micro inclusions, and oftentimes they include high amounts of hydrogen, nickel, and oftentimes graphite as well. Additionally, this diamond has an extra surprise when exposed to long wave UV. The legs of that stellate cloud fluoresce a strong, captivating green. Next up, we're going to switch over to Nicole, who will discuss some exciting colored stones.
Hi, everyone. So like Sally said, my name is Nicole Ahline. I'm a senior staff gemologist at the Carlsbad Laboratory, and I'm going to show you about some cool colored stones and pearls that we see in the lab. Okay, so we'll start here. Pictured here on the left-hand side is a 2.39 carat opal that had a light brownish yellow body color, and it displayed a distinct 6-ray star. And this was examined at our Bangkok laboratory. So while opal is best known for its play of color phenomenon, this opal having asterism makes it exceptionally rare. And standard gemological properties were consistent with opal, an SG of 2.1 and RI of 1.43. And when examined under microscopic examination, this opal had parallel lines with play of color intersecting in a hexagonal pattern. And you can see that in the picture on the right. So unlike asterism and other gemstones, where it is commonly produced by light being diffracted off of inclusions, here the asterism is caused by diffraction off of light from faults or imperfections in the packing arrangement of silica spheres. So also examined at our Bangkok laboratory was this half-carat peribitourmaline that displayed this nice sharp cat's eye right down the center of the cabochon. So standard gemological testing confirmed the stone is tourmaline. And then with LAIC PMS, we performed this for chemical analysis, and we did this to show that there was copper and manganese present, assuring that it was a periba-type tourmaline. And the chemistry analysis also was consistent with periba tourmaline originating from Brazil. So the shortoriancy phenomenon seen here is created by layers of fine parallel growth tubes that were positioned just above the base of the cabochon. So with the vivid blue color, with that well-developed shortoriancy seen in this periba tourmaline and also originating from Brazil, makes this stone a pretty rare find. So seen in the previous two stones that we talked about, phenomena such as asterism and shortoriancy are typically seen on only one side of a fashioned stone. Having one of these phenomena displayed on both sides is very unique, but add in a dual color aspect to it and it simply just becomes a phenomenon in itself. So pictured here is a 5.44 carat double cabochon, and it's displaying a silver cat's eye on one side and a golden eye of almost equal intensity and sharpness on the other. So microscopic examination revealed a strong color zone of brownish yellow, and it was parallel to a near colorless zone. And that near colorless zone actually contained very fine, uniformly distributed growth tubes, and that was responsible for the silvery white eye seen on the left. And now the growth tubes, like I said, did not extend into that brownish yellows area, but when you did reflect light off of that side, it did project it through the parallel growth tubes did project that eye through that colored layer in creating that sharp golden eye. And this is a rare and unique, as this tourmaline is, GIA Laboratory did have the opportunity to witness it again a few years later. So another double cabochon tourmaline was examined, and this bicolor tourmaline weighed about 6.40 carats. And one side was pink and the other side was colorless. And they again displayed two different colored cat's eyes on either side. And so as well with the previous stone, the parallel growth tubes were only present in that colorless portion. But again, when you reflected light through that pink side, it did reflect a nice sharp pink cat's eye to display it on both sides of the stone. Okay, so keeping on the topic of phenomenons, this 1.5 carat black star sapphire was sent to the Carlsbad Laboratory for examination by Elaine Warbach. And while black sapphires are relatively well known, with the common asterism being a 6-ray silver star, they have been occasionally seen to have a 12-ray star or a star that may appear golden. So this star sapphire had two distinct 6-ray stars at opposite ends of the same side of the cabochon, and they both have very distinct colors. So seen on the left, one side had a silver color fading into a little bit of a brown, while on the other end, so on the right side, the stone had a strong golden 6-ray star. And so the body color of the stone, as well as the depth of the star, were the two factors responsible for this asterism that you're seeing. So the silver star was created by inclusions that were right at that surface, which greatly reduced the body color of the sapphire to influence the color of the star. While the inclusions responsible for that golden star were farther from the surface and reflected through that yellow-brown body color, giving it that nice golden asterism. Okay, so at the Carlsbad Laboratory, they received a translucent white cabochon in a yellow metal ring that one could have easily misidentified as moonstone. So in diffuse lighting, the stone displayed a bluish adularescence, and when viewed with a direct light source, such as a fiber optic illumination, the stone displayed asterism. And so standard gemological testing revealed the stone to be actually a laboratory-grown spinel. It had a spot RI of 1.72, and it did have strong green fluorescence under shortwave UV light. So internally, the stone had a dense network of dislocation stringers that were orientated crystallographically throughout the stone, and it's the presumed source of the asterism. And you can see that in the photomicrograph on the left. In the photomicrograph on the right, you can see that there's it's actually displaying this blue metallic coating that was on the back of the cabochon, and this added it was added to create that adularescence seen in moonstone. And I believe this is still the only laboratory-grown star spinel seen by this contributor, as well as one that's imitating moonstone. So another interesting imitation that was seen at the Carlsbad Laboratory were these semi-transparent to translucent cabochons. They had a white body color, and they ranged in size from about 1.5 to 10.5 carats. So from their appearance, again, someone might assume that this might cite idea as rainbow moonstone. But with microscopic examination, these proved to actually just be assembled material composed of a colorless transparent base cemented to a white top and then actually coated in a colorless plastic. So that coating prevented readable RIs for both the top and the base, but in polarized light, a bullseye optic figure was collected on that base, confirming it to be rock crystal quartz. And then as well, it has natural inclusions such as fluid inclusions and reflective particles, confirming that that base was natural rock crystal quartz. And then the top was actually identified as gypsum through Raman spectroscopy. And then while examining that quartz layer, it was actually observed that it was coated with an iridescent coating, kind of like one might see on an Opal ore quartz. And so the plastic coating on the whole assemblage was easy to identify due to it having numerous contained gas bubbles. So to summarize what we have this piece of natural rock crystal quartz with an iridescent coating, and then you have the cemented piece of fibrous gypsum on top of it. And then the whole assemblage was just coated in plastic. And so these are just the type of stones that keep us gemologists kind of right on our toes. So pictured here, we have a cabochon, a double gem specimen actually. So it consisted of an iolite half with a bluish violet dichroic color with red hematite platelets. And this is commonly called bloodstone iolite. And it was intergrown with a sunstone with an orange adventurescence. And that effect was caused by numerous tiny copper colored hematite platelets. So next we'll talk about this clay of color zircon. So green metamic zircons are relatively common in the trade, and stone showing adventurescence caused by tiny discoid fractures that might develop during that metamic breakdown have occasionally been seen. So the Carlsbad Laboratory examined this 1.79 carat oval double cabochon, and this was submitted by Elaine Warbach, and it was identified as zircon with standard gemological testing. And then it displayed a clear play of color phenomenon in both sun and incandescent light. And so seen in the photomicrograph on the left, on the right, the zircon had extremely fine like lamellar structure that appeared to act as a diffraction grating. So as that white light entered the stone, it broke into its component colors. And so also with the stone having really high transparency, this play of color was very apparent in this stone. So opal mined from Ethiopia is known to produce materials with vibrant plays of color, as well as some interesting inclusions every now and then. And so pictured here, we have a 2.68 carat oval cabochon opal, and it had a combination of play of color and chatoyancy. So the image on your left is the cabochon face up, where one can directly see that play of color. And then next to it is an image of that cabochon from the base up, and that depicts that waved structure that produced a sheen like chatoyancy. So if we take a closer look at it, so here in this photomicrograph, you can see that structure. It has, they're using oblique fiber optic illumination to create that sheen like that's visible. And the structure comes just more defined. And so the cause of this structure is unknown, and Raman spectroscopy did not pick up any other mineral present. So it is thought that a pre-existing fibrous mineral was replaced by opal. But even without knowing that, this stone still joins a small group of chatoyant precious opals that we get to see every once in a while. So the last opal we'll discuss is again from Ethiopia, and this displayed an unusual growth structure. So a portion of the opal displayed a wavy layered banding, much like one would see in an agate. And the banded area seen in the photomicrograph on your right was composed of two layers. So one was a harder, translucent, dark brown material with no play of color, and it was alternating with a lighter opaque material that did show play of color. And that a lighter area also absorbed water, which classified it as a hydrophane opal. And so that darker area was left unknown to whether it was also opal or possibly chalcedony, which would be consistent with that banded appearance. And a polished area on the base of the cabochon provided two different RIs for the stone, a 1.43 and a 1.47. The SG of the cabochon was 1.42, which is much lower than the typical SG of opal, which is 2. And that could be due to that hydrophane areas of the opal. And then Raman spectroscopy was done, and it did not reveal any presence of quartz, which isn't surprising due to those two lower RIs at 1.43 and 1.47. So microscopic examination revealed a couple cracks in this stone, and these cracks are actually healed naturally with opal filling. And this was by finding that and observing it, it assisted with understanding the order of events that occurred to produce the pseudomorph specimen. And so the deposition of the chalcedony, so it's thought that the deposition of the chalcedony occurred in order to produce that wavy banded structure, which was followed by occurrence of stress fractures that laterally shifted the stone, and that was creating these micro faults that you can see in these two photos. And then these faults are then healed with a secondary deposit of opal, which also replaced the chalcedony while preserving that original agate structure. So this stone is pretty fun. So this is a 3.35 carat stone that was submitted to the New York lab. And generally when one thinks of assembled stones, you might think about the ones that we just talked about, a stone that has 2 or more pieces of material that are joined together in a layered manner. But pictured here is actually an imitation emerald, and it's composed of 5 glass segments that make up the pavilion of the stone and the crown. And they actually surround a rectangular barrel core. So an RI was taken over all 5 segments, so 4 in the pavilion, 1 for the crown, and it got refractive indexes of 1.61, an SG of 2.66, and then where all these pieces actually came together, they had a weak white fluorescence that followed those cement planes. And so here we can see on the left, we can see where areas of the cement places are intersecting on the pavilion. And the photomicrograph on the right shows natural dendritic flakes and fingerprints. That is in that natural barrel section that makes up the core. And then also what revealed were large gas bubbles were observed in those cement layers. And then when the stone was immersed, the green color of the stone was easily shown to be derived from the 5 glass segments. And to confirm glass, Raman spectroscopy was performed on all 5 segments, and it produced a very typical glass spectra for all 5 glass spectra, and then there also were detected peaks of beryl for that core. So to better understand and just comprehend the structure of this stone, they created a really nice diagram for us, and you could kind of understand how a stone like this might be created. So first we have that gray box right in the center, and that's representing our natural beryl core. And then it got one side attached with glass, as you can see by that lime green in the box label number A. And then it was cut down a little bit to make room for that second glass segment, the teal that you can see in C. And then again, it was cut down to make room for segment 3, the darker blue. And then the process did one more time for segment 4, that purple. And then the final segment is presumed to be added last, which was presumed to be added last, was the crown, and just finishing up the creation of this very cautionary assembled piece that we saw. So this rough emerald weighed about 9 grams, and it was sent to the Carlsbad laboratory for examination by Lucas Fazzari. And when examining emeralds for origin, multi-phase inclusions are key indicators for origin determination, and typically require higher magnification, more maneuvering of the stone to get a more precise view. And this emerald rough, identified using standard gemological properties, had an eye visible mobile inclusion consisting of a CO2 gas bubble and a salt crystal suspended in fluid. And so the origin was determined to be Columbian, and that was supported by the jagged 3-phase inclusions, as well as some pyrite and calcite present. And so here we can see, there we go. So here we can see the bubble moving, which is super cool. And it was actually quite large. The bubble itself measured about 4 by 3 millimeters. Okay, so this emerald weighed a little bit over 1 carat, and it was actually obtained by GIA's, it was obtained for GIA's permanent reference collection. So when it was being examined for documentation, you can see this unusual curved zoning was noted. So gemological properties, again, were consistent with emerald. It had an RI 1.589, 597. It did have natural emerald inclusions that were pyrite, reflective thin films. But that S-shaped green color zone throughout it was just highly unusual, considering emeralds generally have more of a planar or angular color zoning that is related to the crystal's morphology. So one possible explanation is that compressed geological forces cause shearing along the emerald crystal's basal plane. And in the photomicrograph on the right, you can kind of see, so these are pyrite fragments, and they kind of support this idea. So this appears to be one single pyrite crystal that has been sheared and then slightly misplaced by a lateral shearing movement throughout the emerald. And the exact cause of this unusual zone is still unknown, but it does show that there are still complex geological conditions out there that are yet understood, but we do get to see it in some of our beautiful gemstones. So pictured here, this is a 69 gram quartz crystal that was reported to be from Colombia. And it was submitted to our Carlsbad lab for scientific examination by Ron Ringsrud. It was a well-formed, singly terminated crystal with high transparency, and this allowed for its vibrant green emerald inclusions that you can see on its base to be easily visible. So the emeralds, it is presumed that the emeralds did form first, and you can kind of see that evident by how the emeralds are there at the surface of that quartz that you can see in that photo micrograph on your right. So again, they presumed to be grown first, and the quartz itself measured about 74 millimeters long, and that the largest emerald in there measured about 23.5 millimeters long. So it's actually they're actually quite large inclusions that we're seeing in the sky. So GIA had the opportunity to examine what in the trade is called eye sapphires, courtesy of GIA Knowledge. And all of the samples were opaque, and they were cut into these cabochons to display this radial pattern. And they're often accompanied by concentric color zoning, and they were all in the combination of blue and white. And so when growth pattern is seen in minerals, they're commonly seen in minerals that precipitate from fluids such as silica, but prior to examining these, they've never been observed yet in Corundum. So Raman spectroscopy confirmed that both the blue and the white areas were Corundum. Diaspore, which is the common secondary mineral found in Corundum, was also identified in the white areas. ICP-MS was performed on the stone pictured here, and it was revealed to have very low iron content, so it didn't come from a magmatic source, or is presumed to not come from a magmatic source. And it should be pointed out that this stone was not subjected to heat treatment, because Corundum heat treatment is a common practice and it is accepted in the trade. And this is evidenced in the photo micrograph on your right, that epigenetic yellow goethite that you can see in that fracture. If that stone was heated, even at relatively low temperatures, that goethite would actually alter to a rust-colored hematite. So next, we'll talk about this yellow. It's a little bit over 40 carats yellow carat Trapecia yellow. My goodness, a 40 carat Trapecia yellow sapphire that was submitted to our New York lab, and it was actually submitted as a star sapphire. So while Trapecia patterns are well known to occur within emerald, and they have been documented in Corundum, they're typically documented in rubies. So the fact that this was yellow was pretty interesting. A small core was area that was parallel to the C-axis formed in the center of this formation, and it can be seen in that the upper left-hand corner of the photomicrograph on the right. And so the triangular growth sectors had a yellow body color, and they had inclusions such as fingerprints, two-phase inclusions, and reflective thin films. But the reflective thin films that were actually seen in the white spokes were actually parallel to that center core. So both the triangular sections and the white spokes were very different. And so that different in inclusions and that color suggests that the sapphire crystallized from the core outwards, but with the sectors and the arms growing concurrently, but at just different rates. And so another cool trapecia-like stone that we saw was submitted to our Bangkok laboratory. And so this about 5 1/4 carat ruby was examined, and with chemical analysis and gemological observations, this ruby had an origin from the Batakuni mining area. And when examining right under the table of this stone and depicted in this photomicrograph here, it had a very well-formed six-ray pattern. And so this trapecia-like ruby is slightly unique, for this trapecia is an inclusion and not the whole stone like we previously saw in that yellow sapphire. And so each arm of the structure is aligned perpendicular to the hexagonal growth, and it consisted of minute particles with needle-like inclusions as well as small thin films. And the center, or the core of this trapecia, is a group of colorless and black crystals, and they were identified as feldspar and graphite by Raman spectroscopy. So this one, very fun. Okay, so this picture here is a unique fish. It is a fish-shaped brownish orange pearl, and it weighed about a little over 2 carats, and it measured 21 millimeters long. And this was examined at our New York laboratory. And then this pearl had a very uncanny likeness to a fish. It always brings a smile to me when I get to see this photo. So the entire nacreous surface was composed of overlapping platelets with no indications of work, such as polishing, nor were there indications of treatment such as dyeing or coating. And then with EDXRF chemical analysis, there were higher levels of manganese, which supported that this was formed in a freshwater mussel. So using real-time microradiography and X-ray computed microtomography, it revealed clear natural growth structures that conform to the pearl shape. And so here's a 3D rendering of the X-ray CT data, showing just the remarkable likeliness of just a swimming fish. So the Pinctada maxima is the largest species in the Pinctada genus, and natural pearls may form within Pinctada maxima as a result of some trauma to their mantle. And natural blister pearls have been documented, and some have been documented that encase these dead pea crabs inside their shells. And the crab, this crab is known to live in symbiotic harmony with some 85% of Pinctada maxima, both wild and hatchery grown. Pictured here in the 3 images below is a blister encrusted pearlfish. And what a pearlfish is like a slim eel-shaped marine fish. And this observed toward the hinge of the Pinctada maxima shell. And the partial microradiographic image all the way to the right clearly displays the fish's skull and vertebrae. And so this just attests to their interdependent living of the fish, as well as with numerous other creatures that dwell within the valves of Pinctada maxima. So non-nacreous conch pearls from the Strombus gigas are known mainly for their attractive pink color and distinct shimmering appeal due to the characteristic flame structures on their surface. The New York lab had the opportunity to study part of Susan Hendrickson's conch pearl collection, and among them were a few rosebud specimens, and they ranged in size from about 93 points to about 14.5 carats. And rosebud is the term most commonly used to describe the characteristically shaped freshwater nacreous pearls. And this was the first time GIA has examined conch pearls with such shape. So in the tile image on the left, that top left image shows an American freshwater pearl exhibiting a rosebud form. And then the other 3 are the conch pearls that were examined. And so all the rosebud conch pearls examined had clear differences in bumps and ridges, with some more rounded and spread out than others. And this is very typical of a rosebud pearl form. And the photomicrograph that you can see on the right depicts the characteristic flame structure that was seen in at least one spot on every pearl. And so Raman spectra of the pearls did show aragonite and natural pigment peaks as expected from pearls from the Strombus gigas mollusk. So pictured here are some interesting inclusions documented by the GIA research team from amber that was collected from Burma. And so these specimens potentially preserved evidence from biological environments of 80 to 100 million years ago, which is significantly older than the ambers from the Dominican Republic, as well as the Baltic region. So that top left photo micrograph depicts a flower still attached to its stem, and you can kind of see there's like a little small bug on it to the right. And then the top right photo micrograph is of a spider with plant debris and you can just see that there's still fine details such as the spider's hairs and different sets of eyes can still be seen. And then the bottom 2 photo micrographs is of a fly. And so the right shows, or the left shows all the features still intact, even its wings. And then right next to it, you can get a close-up view of the fly's eye. And these ambers just had excellent preservation. So this was a 19 carat, about a 20 carat actually copal. So a copal is a natural resin that is much younger than amber. And this copal contained a very large eye visible and very well preserved mushroom. And it's reported to be from Mexico. And so the cap of that mushroom was measured about 5.5 millimeters in diameter. And what is interesting about the significance of this piece, which kind of goes outside or beyond a gemological standpoint, is that copal was used for many years by some indigenous people in Mexico and Central America as incense for ceremonial purposes, such as the sacred mushroom ceremony. So muscovite is a rare mineral closely related to the mineral taphite by composition and is slightly sought after by rare stone collectors. And so this 86-point muscovite, which was identified by Raman spectroscopy, contained numerous etch tubes that broke the surface with fiber optic illumination, and the etch tubes displayed a really nice iridescence. And so this was the author's first, and I believe only time examining a muscovite that displayed any type of optical phenomenon, at least since this microworld note was written. So at the Bangkok laboratory, this 14.5 carat stone was submitted for examination, and it was bicolored with zones of blue and red. It had an RI of 1.718 and an SG of 3.6, confirming the stone was spinel. And then the red portion fluoresced medium red under long wave and was inert under shortwave fluorescence, and the blue portion was inert under long wave and shortwave UV. Microscopic examination did reveal natural inclusions, and then with the aid of Raman spectroscopy, there was actually no indications that the stone saw any heat treatment to aid or alter the color of this stone. And there was also no indication of dye present on either side. And so the gemologists collected UV visible spectrum on both sides to determine what was the cause of color. And so that blue side had absorption features caused by the presence of iron, while that red side had absorption features caused by the presence of chromium. So this next piece serves as a useful example of why turquoise is routinely treated. So examined at the Carlsbad laboratory was this natural untreated bluish green turquoise bead necklace. And so during examination, some beads showed a discoloration pattern that resembled fingerprints. And you can see it in the photomicrograph on the right. And so the beads had an RI of 1.6 and then no polymer related peaks in the infrared spectrum, which ruled out the turquoise beads being polymer impregnated. So untreated turquoise is porous and often absorbs skin oils and other contaminants. So it's thought that the fingerprint pattern could possibly be a result of glue or another impurity present during that initial handling, and then preserving that pattern with where during time and where that discoloration of the bead made it more distinct. So the last piece we'll discuss is the 58.3 gram jadeite bangle, and this was examined at the Carlsbad laboratory, and it showed a very unusual green color through the center of the piece. So it was model weight jadeite with green patches, is not uncommon and is naturally occurring with chromium, or it can be artificially induced with dye. So with the aid of the handheld spectroscope, there was no distinct features for either chromium or dye, which are usually present in that red region of the spectrum. And then under magnification, that green zone followed a textural zone that was much more finer and denser than the other portions of this bangle. And there was no indications that this might have been repaired or manufacturing could have been performed. But when the green color was actually proved to be a flash effect that was visible when the viewer's line sight was parallel to that textural zone against the light background. And then when that background was dark, that flash effect was an orange color. And you can see that in that bottom right photomicrograph. And so polymer impregnation was confirmed with the aid of FTI spectroscopy to be present in this jadeite bangle. And those are our fun pieces.
All right, thank you, Nicole and Sally. So we have some time right now to go to some questions. The first question that we wanted to ask is about that color change diamond that you talked about, Sally. And so one question from Elsa was, they asked, what is the country of origin of that diamond? So, are there diamond mines around the world that are more known for producing, I guess, color change type diamonds?
Thank you, Aaron. And yes, actually, the violet diamonds that we see out of the Argyle mine, oftentimes those are blue to gray under daylight, and then they switch to a more violet color under incandescent light. The first diamond I showed was a violet diamond that had so much absorption that it appeared fancy black face up. But if it was cut differently, or if it had slightly lower absorption, then you would probably be able to see that sort of color change in one of those Argyle diamonds that often go from green and daylight. I'm sorry, gray to blue and daylight to violet. Now the one I was presenting earlier that went from pink and daylight to a purplish gray and incandescent, that was a slightly different. That was a treated diamond, and it was rather unusual because oftentimes when people treat a diamond to make it appear pink, they will irradiate and then do some post irradiation annealing. And what they do with the subsequent annealing is that they cause those nitrogen and vacancy atoms to find each other, and then that causes the GR1 to decrease in intensity. So this was a very unusual treated diamond that you had both a significant concentration of NV centers, but also a significant concentration of GR1 as well, so that you were able to have decent concentrations of both of those defects in order to see the purple gray color in incandescent light, and then also the pink color due to the NV centers in daylight.
And so that color change diamond, is if I recall, it was more of like a reverse color, what we call reverse color change, right? Where it had more of a warm color in daylight.
Yes.
Can you describe, like, are color change diamonds common, and what are sort of like the typical color ranges that you see for color change diamonds?
Well, this one in particular, it was unusual because what was really contributing to the pink color in that diamond was NV-related fluorescence. So we weren't looking so much as at an absorption, so much as a fluorescence effect caused by this very pronounced contribution of the strong NV centers to create that. Most of the time, if you have a very pink diamond colored by NV centers, you don't have also a simultaneous GR1 band that creates that blue to purple color in under incandescent light. Another branch of color that are in this sort of family of color change diamonds are chameleons, and we can see those change color with the application of heat or sometimes with time. The ones that I'm speaking of from Argyle mine and this treated diamond, they exhibit more of an Alexandrite effect.
Okay, thanks, Sally. Now for you, Nicole, that moonstone imitation piece was fascinating. The one that was made of the quartz and the gypsum and the iridescent there.
Yes.
But it seems like an awful lot of effort to go to imitate a moonstone. Now, can you maybe comment on how common are moonstone imitations, and why do you think somebody went to all that effort to imitate moonstone?
I think people have many different reasons in order to do it. Maybe they were just trying to make something and see what came out of it. But I don't think I have a really great answer on how to answer that, but other than just test and fail to see if they could make an imitation. I personally don't think I've seen a lot of moonstone imitation. The majority of it has just been coated to give more of that agilurescence look to it. But I think that people could do it for multiple reasons.
And the similar thing with that barrel that was assembled with 5 glass pieces. I mean, how common are assembled pieces, and are they, you typically think of assembled pieces like a doublet or a triplet or something. Is it common to see other things?
Yeah, that piece was pretty crazy. I've always blown away whenever I get a chance to talk about it. But yeah, I think anytime you see a piece come through, you always have to be aware of it's being assembled, especially Opal. We always check our Opal pieces, especially when they're bezel set to check for that assemblage. And I think that they're very much still here and very much still present in the trade. And anytime you do get a piece, we are always consistently checking for it to making sure a piece is or is not assembled. So very much still present and coming through.
All right, thanks. Now, one more for you, Nicole. You presented on that fascinating barrel or the emerald with the mobile fluid inclusion. Do we ever see that sort of thing for natural corundum? This is a question from Christina Bright.
Could you repeat the question?
Do we ever see mobile gas inclusions in natural corundum?
That are eye visible? I'm trying to remember if I've ever seen one that is eye visible. I'm assuming that it could definitely happen. I don't think I personally have witnessed it. I asked the question to you, have you seen one?
Not really so much an eye visible one. I mean, in the microscope, yeah.
Yeah, same.
Yeah.
I'm trying to think if I have one or if I've observed one. I know that you can commonly see it in quartz a lot. Definitely that was the first and only time I've seen it in an emerald, and I can't think of a time if I have seen one in corundum.
I've seen one when I was in Mogok in a spinel, and that was pretty fascinating, actually.
That sounds like it would be a very fascinating piece.
Okay, Sally, back to you. A question from Miguel Zanetos. Is it possible, he says, on field or with a miniature gem laboratory to identify natural or treated color?
That can be, it depends on the type of diamond, and oftentimes we do need to run advanced testing on it to determine if a diamond is natural, treated, or laboratory grown. We do have a number of seminars that are available to help you get some hands-on experience with known samples that are known natural, known color treated, or known laboratory grown. And if that's available, I would encourage you to try that. But oftentimes, in order for many many colors of diamonds. It's oftentimes we do need to run some advanced spectroscopy on it. If they are in the colorless range, it can be a little bit more straightforward. There's a number of items on the market to help certify if verify if a diamond is treated or natural color or laboratory grown. It gets a little bit more complicated for looking at fancy color diamonds.
All right. Thanks, Sally. And so I think we're getting on pretty late, so I think we should probably start to wrap it up at this point. And if you're in town in the next 2 weeks or 2 weeks from now, we'll have another one of these knowledge sessions where our colleague Wim Vertrees will be talking about playing the blues, an overview of sapphire treatments. So please join us for that one. And if you have any questions in the meantime, please join us on Instagram, Facebook, LinkedIn, and Twitter, and we'd be happy to talk to you about anything related to gemstones. Please join us again in 2 weeks from now. Thanks.